Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We are extremely pleased to have Helmut Seidel with us today. He's a professor at the Technical University of Munich. And as we were just discussing, there are several other people like Tobias Nipkov, Javier Esparza, Andrei Rybolchenko, people that we know that work with him as well. And today he's going to speak about static analysis of interrupt-driven programs. So Helmut is here today. He's going to meet with most of us. And he's here for the next couple of weeks. So there's also opportunity for us to meet with him again. Maybe go to IAC or have him come again. Welcome.
Okay. Yeah. So thank you very much for the introduction. So this kind of, this line of research, which I want to tell you about today, is at the kind of cross point of two research projects which we do in my group. So one is with Faisal Voidani together. This is within a project with companies from the automotive area and also the avionics area, which is called MBAT, Model-Based Analysis and Testing, where we are on the analysis side. And our goal there is to analyze control software or any software for cars or for planes. And that is, and this kind of software is so interrupt-driven. An interrupt-driven paradigm is kind of a central concept there in the automotive industry. And then there's also Peter Lammich and Markus Müller-Olm from the University of Münster. With them we have a DFG project very more on the theoretical side, which is about exploring paradigms for parallel programming and see whether one can design and realize very precise, or in some sense theoretically complete analysis techniques for these. And so we looked at this interrupt-driven programs therefore are interesting in these two respects. On the one side in the practical area, but also from a theoretical point of view. So now, why doesn't it stopped working? Maybe let's check. So here is a car, and there are all kinds of things which are all kinds of sensors, and all these sensors produce signals, and all these signals somehow must be handled. And if it's some of these signals have to be handled in a time-critical fashion. So for that they have come up with kind of a standard for real-time operating system, which is this OSEK AUTOSAR. So AUTOSAR seems to be the standard, and OSEK kind of an implementation of it. So this is the current state of the art is that this operating system runs on a single processor. So, and this single processor is meant to process all these incoming signals and react to them in a timely fashion. And in order to do so, it needs kind of a deterministic scheduling strategy. So it cannot kind of do some kind of arbitrary scheduling which tries kind of online best possible choice. This would not allow them to give guarantees that a certain signal is reacted to within a certain time frame. So therefore they have a particular deterministic scheduling strategy, and this is based on priorities. So if there is a task running and a higher prior interrupt is coming, then the task will be interrupted. And these kind of how these priorities are not statically assigned to processes. There are also something like static static priorities of tasks, but these priorities may dynamically change. And the protocol by which priorities may change at runtime, this is done by means of the priority ceiling protocol. I don't know whether have you seen that kind of protocol before? So I will explain. So here is perhaps a little bit of an explanation. So here assume you have tasks running at 3 different priorities. So then you could, this is perhaps the main task, and there could be an interrupt at a higher priority, then this would run, and then an interrupt of an even higher priority may arrive, which then again interrupts. And then once the interrupt has finished, then the interrupted, the next the next tasks with the next second best priority will proceed until in the end the main task is executed. And now what does the priority ceiling protocol? So there it is based on a concept of resource. And the resource is some kind of abstract thing like A. And if you may acquire a resource or release the resource again. Now if you, by acquiring a resource, you may increase your, give a current priority to a higher priority. And when you release the resource, you fall back again to the lower priority. Now the question is, what kind of priority is attached to a resource? And this is done in the, I think, quite cute idea there is that the priority of a resource is the maximal priority of any task who wants to use this resource. So by that it means whenever you acquire the resource, you cannot be interrupted by any other interrupt or task which also wants to have this priority, this resource. Okay?
So this is dynamically done or statically?
There is a kind of, they call it oil file, where you statically specify your tasks and the resources and which tasks will acquire which resource. And then you can statically find out what is the priority of the resource. And then when you dynamically execute the get resource, your priority will dynamically be increased. So by that, you get by acquiring a resource, you get a temporary protection against interrupts, whose static priority is less than the priority or equal to the priority of the resource. Okay, so that's the idea. And
so I have one question. So is the request, if a task requests for a resource, is that an interrupt or is that not? Is that an interrupt?
No, the interrupt is kind of, you could think of it, a signal comes in, then there's a signal processor which creates the interrupt, and then the interrupt tries to run, and then it has a given static priority, and then it may run if its priority is larger than the priority of the currently running task. If not, it has to wait. So the interrupts are created by external sources, if you like. So that therefore this means that they can occur at any time. So it also, technically, it also means that certain kind of tasks are cyclically scheduled by, and that means that they are triggered by a timer. And actually, the programs are in such a way, so at least if it's in the main control loop, that it is a loop, and there is this cyclic scheduling. But for us, we see as a program, so we do not analyze the real time, the timing behavior. So for us, it's just that something which may occur anytime.
So yeah.
Is the priority definition mutually recursive, or is that maximal static
Yes, maximal static, that's true. It's maximal static priority of all tasks that using that.
Not mutually exclusive.
No. And that is the ceiling priority. And that, then at runtime, you dynamically may increase your priority to the ceiling priority of all the resources. You may have acquired several resources, then you take the maximal priority of all of these ceiling priorities, of all these resources. So in some sense, the resources have kind of names, and but it is what matters is the ceiling priority attached to the resource. Okay? And so this, because a task, and now an interrupt also we can think of as a task only triggered by an external signal or so, cannot be interrupted by something which has the same priority, only by something which has a higher priority. Okay, so in that sense, in this particular world, access to data structures is protected by resources. So it's something different, like this locking and unlocking thing, which we know from, which we typically know from concurrent programming. Okay, so now, if what kind of bugs could occur in such kind of programs? So clearly, there are the usual bugs, and that is probably the most important one is protecting against floating point overflows, or perhaps also integer overflows, because they have kind of, it seems at large. So I must say, when I speak about usually or currently, perhaps this is a little bit exaggerating, because these car vendors are very reluctant to expose their software. So there's, you know, this thing with the intellectual property. This is very strong there. So we tried to extract from them as many benchmark examples. We did not get so many, but they told us at least that this could be errors. For example, if you do some kind of numerical computation in a control loop, you might kind of apply some kind of linear filters or so. This is floating point operations, and so there could be floating point bugs. So this would be some kind of errors. Another thing is there can be also, in some sense, since an interrupt may occur at any time, in some abstract way you can consider it as running in parallel to your software, or at least the actions of an interrupt can occur any time, and you might protect against there might be bugs in such form that your data are corrupted by an interrupt who also accesses these data. So this is the things, and then there is such thing which is perhaps the most also, and sometimes the programmer might think that his task or a function in his task is executed transactionally. And that this might not be true, because in between another interrupt may acquire or have a priority strong enough to interrupt. So these would be the kind of bugs we would kind of go for. Now, what is a data race? In a certain sense, you might think there cannot be any data race philosophically, because it's a single processor machine. And so everything is sequential, and everything is in some sense even deterministically sequential. So data race is something where something is an error due to non-determinism. But one might think that there's something, you could interpret a data race as a lost update. So this means your task writes 1 into a variable x, and then later will use this variable x, perhaps. But in between, without any, there could be an interrupt which just modifies your x, so you cannot rely on the values of variables. This one might consider as a data race. And what does the transactionality mean? So actually, also in ordinary concurrent software, data races are not are only well, it is not so. Actually, data race does not constitute a bug in a concurrent program. It's only an indication that it might not be wanted by the programmer. And it is even not sufficient, because sometimes one does want that certain actions are executed atomically, one after the other, and not only that each individual access to a variable is protected. So like here, one might want that here this assignment should be immediately followed by that assignment. Why? Because then, if this is the case, hopefully the result of y afterwards will be 0. But if the priority goes down in between, then protection is low there. This means somebody else could change the value of x or y, of y, and then it would not be the case that afterwards y equals 0. Yeah? So therefore, transactionality is actually I would consider a more serious problem for concurrent programs, and for these kinds of programs also.
So here, do you think about variables x and y as associated with resources, or no?
No, well, these are kind of just variables. They are not resources. So in order to increase the priority, you should additionally try to acquire a resource. Yes.
I see. So one should think about resources as logs associated with these variables.
Yes. So these are the kind of the variables which have the data, and then there are resources which are kind of abstract entities, or a separate data structure like a log. Okay, so yeah, here it would be so if priority goes down in between, some variable could be modified, and so in the end, your invariant which you had in mind would be violated. Okay, so now so the goal is to analyze such kind of data races or transactionality, or even so that would be kind of how would one do it? So the first is these resources. So in some sense, you could think of that the resources which you have acquired are a local variable. So this is a set. You can maintain them in a set, and you could consider them as local to a task. So it means that even if an interrupt occurs, it will not have access to my locally acquired resources and will not kind of modify them. So in that sense, interrupts do not matter for when I want to determine the set of possibly held resources at the program point. Yeah. So, but so this means it turns. So in that sense, analyzing the resources which are possibly held by a task is not so complicated, even if there are interrupts. Yeah? And once I know the sets of held resources, I can determine at the program point the ceiling priority when reaching this program point. Yes?
So why should a held resource look like a local resource? Because the ceiling priority is defined only in terms of the static priorities, right?
Yes.
So some other thread, dynamic priority may go higher.
Yes.
It may continue to access this resource. So,
but then, if I ever will run again, that thread will, that interrupt will have released the resource again. Otherwise, I will be stuck. So consider program point 1, 2, 3. So I reach program point. I'm at program point 1. At program point 2, I want to acquire A. So now, before I cannot, maybe I will, an interrupt occurs in between and somebody else acquires A. So then an interrupt occurs, so that's one thing, and A is acquired. Then the interrupt occurs, I will only be able to continue with my computation if the interrupt has finished. And when the interrupt has finished, it has released the resource A. So this means for me, when reaching program point 2, whether the interrupt occurred or not does not matter. Whenever I will reach the program point for where I can acquire A, I will acquire A. So I just the idea therefore is I can analyze my task as if it were alone in the world, without interrupts. Okay? And by that kind of determine the ceiling priority for every program point, hopefully. And then once I know what kind of resources may be held by at program points, this hopefully helps me to analyze these data races, and then also to do the transactionality analysis. While for the so let us take a closer look at this resource analysis. So the first thing is this one, what I just tried to explain to you, that preemptions by means of interrupts does not influence the set of resources I hold. Only it could affect it in one way, in that sense that perhaps I'm interrupted by an interrupt which does not terminate. In that sense, because then I will not reach the end of the interrupt. But this one can over-approximate by assuming that every interrupt possibly terminates. And in this kind of real-time context, they typically do not write interrupts which do not terminate, or that would be a serious bug. So we may, at least optimistically assume that every interrupt will terminate, and that means that we can ignore interrupts when we only for the task that we want to determine the set of possibly held resources. And then so that is perhaps also an important this is not kind of our invention, but a kind of a guarantee. This what the operating system there gives, that when a task is started, then it starts with no resources, and when it terminates, it will release all resources. And then, so that is this is the good news. So for analyzing resources, we have an ordinary interprocedural, if you like, analysis. Interprocedural because it is these kind of programs are typically written in C. So you could have functions and you could have function calls. In practice, these software will not have recursive functions, but the same function could be used in different contexts. And different context means here, for simplicity, if we for a moment ignore data, different contexts means a function could be called by different tasks, and at program points where there are different sets of held resources. So in that sense, we kind of have to analyze functions with a context. And for simplicity, one would at least, so if one just looks at control, one would at least have to compute summaries for functions depending on the set of held resources when the function is called. And it may also be so that when a function returns, it has not released all the resources. So it might have increased the set of resources. Or it might only release and not acquire. So it's really an interprocedural analysis.
So preemptions might matter in the sense that they might change your state?
That is true. They may change the global state, and if the task reads the global state and control flow depends on global state, then this will fail. So for the moment, we just assume that there's no global state. Or perhaps I can tell you immediately how we deal with that. So we deal with that in our analyzer Goblint by having for globals, we maintain a flow insensitive invariant. So that you kind of accumulate all possible updates to the variable in one, just accumulate them. And then you read from this kind of global single invariant. And then with respect to that, once you have this global invariant, then all the things are kind of decoupled again, and you again can use just a plain interprocedural analysis. Yeah. Okay, so then it is clearly so that program points could be a single program point in. So you have a procedure. It could be called with different resource sets, but still there could be different flows reaching a program point, so that you have arrived there with different sets of resources. Then you could do two things. Either you try to be precise and keep all these sets of resources separate. But these little examples, or the indication which we have, is that this is not worthwhile doing so. So you could just do try to analyze those resources which you definitely will hold. So do kind of a must analysis. And it seems so that most of these programs, at a given program point, they always will have the same set of resources. So in that sense, the must analysis will be the same as the real analysis. And so if the assumption is that the set of resources depends on the calling context and the program point, but not on the flow, how you have reached the program point, then it turns out that you have something like a GAN-kill framework, because you have this set of held resources, then you have a get resource, this increase something, and you have a release resource that removes something. And that's all. And so it's just GAN-kill, and it makes it even simpler. Interprocedural GAN-kill is very simple, so you can do a very fast analysis for it. Now, what is a data race? For that, to formally define it, we define two things: the defense priority and the offense priority. The defense priority of a variable x is a program point might be reached by a dynamic priority where the variable x is accessed, and then there could be different program points with different such priorities. You take the minimal one, because the minimal one is that which might be attacked most easily. And which is the minimal, the access with the minimal dynamic priority is that one which is the most vulnerable, if you like. And then for the offensive priority, you try to find the strongest attacker, and that is the one with the maximal static priority, because the interrupt when accessing X must be admitted, and it's only admitted at a program point if its static priority is strong enough, stronger than the dynamic priority. So therefore here you have static and there dynamic. And then simply a data race occurs if the defense priority is less than the offense priority. If they would be equal, then it means that, an interrupt of equal priority is not able to interrupt. So therefore it must be larger. Okay, so in that sense, as soon as you know the the priorities when doing an access, you can determine that, and then so data race easily follows once you have the resource analysis. Now for the transactionality analysis, so this is a little bit more contrived, because now you have to track somehow how the priority evolves over a certain period of time. And for that, so here, for example, think of this would be kind of the critical section which you want to check for transactionality. So the priority before accessing a variable does not matter. And the priority after doing the last access also does not matter. But the priority in between matters. So you have to check whether between the first and the last, the minimum of priorities between the first access and the last access. And in this case it would be 2. And in order to get that, you may just look at one function. You do not know where in a critical section it will be called. It could be called before, so in the beginning of the task, and so the first access could be within the function call, but the last access could be outside, or both could be inside, or only the last is inside, or it's in, so there are several conditions which could occur. And these correspond to these 4 accumulated priorities. So the first is the minimal priority after the first access one observes in the given fragment of program until the end. So the minimal priority after the first access, because some more accesses could come. Then you consider the minimal priority before the last access. So that means if you have the last access, then you want to know what was the priority. And then the minimal priority overall. So this means if a function is called in the middle. And so this gives, in this case, one obtains these four numbers. Okay, so that in this sense, the summary of a function then will be a mapping from the resource set, because the priorities depend on the resource set, which are held when the function is called, and these 4 numbers. And now, if you want to do an analysis for that, you kind of must compute with these summaries. So, for example, you must be able to implement composition. So, and that is, the question is, if you have these 2 tuples of such 4 numbers, can you compute the corresponding 4 numbers for the composition? And here is how you do it. So for the first one, for the critical, the maximal priority in the the minimal priority in the critical section. Well, how would that be? So if this is the first, the prefix, and this is the suffix, and you think of the critical section, so it could be that you have to take this one, and you may proceed here. So this means that the first access is here, and the last access is there. You might also take into account the minimal access where it is the first and last is here, and there's no access there. But if the first and last is there, then this priority will typically be larger than the priority in this larger interval, so you need not take it into account. You see, because you want to have the minimal priority. So therefore, you just take these 2 values, y and b, and take the minimum. Okay, and the same you can do for all the other numbers, like here, or there, or there. This one is particularly easy, it's the whole, so you take everything there and everything there. Okay, and then now you have this composition, then the only thing what you need to know is about, what kind of 4 tuples you have to assign to individual edges in the control flow graph, and if an edge is executed at priority p when no access occurs, then I guess, so then these numbers occur. So this means it does not affect these 3 values, but may affect that one by giving the contribution p. So so in essence, then the transactionality analysis would compute summaries for every function, and that is for every set of resources, it has to provide these 4 numbers, and that is, you can use kind of a summary-based interprocedural analysis, and that will run linear in the size of the program. So it may quadratically depend on the number of priorities which you have, and exponential in the number of resources. So this sounds a little bit frightening. Yeah, why exponential? Because you kind of have to tabulate for every set of resources. So that sounds frightening, but so it seems that people do not, so far, I would say. If there is some kind of programming possibility, sooner or later people will make exhaustive use of it. But so far, it is not very, perhaps programmers are not so familiar with this concept of resources. They are afraid of that, they use very few. So therefore, as long as they use very few, this is not a problem. Or if they use more, that would mean it would mean that you would have at certain program points more than one resource. And that means it's not so clear whether programmers would like just to increase your dynamic priority. It might not be necessary to hold several priorities several resources at the same time. But if so, then the only hope there is that one only has to do this tabulation for those sets of resources which really occur in the program. If they don't occur, you don't have to tabulate them. So in that sense, again, one might think that this exponential is not too bad. Okay, and then once if you want to find out whether a function is transactional when called on a set of resources R, then you only have to you check. You can determine that by means of that tuple. You only have to check whether this critical the minimal priority, which is guaranteed throughout your critical section, is larger or equal to any offense priority for any variable accessed in between. So that's that would make this transactionality analysis practical. So and now how did we? So this has been implemented in our analysis framework Goblint. I will talk about that perhaps in this workshop, where some of you will also be in September. So there I will talk a little bit about this analyzer generator. This is not meant for directly for interrupt. So it's just a general interprocedural analyzer, but it can also be tweaked to do this kind of analysis. And I told you that the globals we deal with by this global invariance, so this flow insensitive unique values, and that is kind of reflected by a particular fixed point algorithm which supports such kind of analysis together with interprocedural context-sensitive analysis of local data, of thread and or procedure local data. And so this is one of our precious larger, or one should say not too small example programs. I think it was kind of it is kind of software which controls a roof which opens and closes when you press a button, and it could be analyzed quite fast. The problem with that one is that it is quite large, and the analyzer eats it, but it uses few resources. Actually, it uses no resources. It has several interrupt levels, but it uses no resources. And one might wonder how can programs survive without using kind of synchronizing. So here is and I come to that in a minute. So there are kind of, then we had we received some benchmarks which are more realistic and they use resources, but only very few, 2 or something, and they are also very small. So in this sense, they do not say much about the quality of the analyzer, but it can only be seen that one implements the features correctly. We had a kind of synthetic benchmark where we kind of tried deliberately to increase the set of interrupts and the set of priorities, and then clearly one observes that that the runtime of the analyzer also increases. So this is expected. In particular, here you have 1,000 priorities, which is rare. So now, as I told you in the sunroof thing, people use no resources at all. How can they synchronize between interrupts and tasks? And they told us what happens is that people have written this kind of software long before some managers came up with the idea of using OSEK. And so what poor programmers were forced, now you have to do OSEK, but they had running software. What would they do? They would try the minimal change to let it run under this new operating system. And so there we found kind of handcrafted protection against interrupts. Here's one such example. That is perhaps, so my conjecture is that it's not too untypical. So the idea is you have some low priority task and you have high priority interrupts. And how can the so the high priority interrupt, if it interrupts, it has the all control, so it need no protection, against the task. But how can the low priority task protect against the interrupt? And so they have sometimes seem to introduce flag variables which are set to some value. And then they do what they ever want to do. And then comes the interrupt and it checks the flag. And if the flag is 1, is set, then the interrupt kind of does nothing. It's ignored. It hopes that it will be kind of former or later occur again. Yeah, because perhaps this critical section is not too long. So in that sense, nothing happens here if the flag is set. And if it is not set, then they do something. And that means it can only execute out down there. Or before, maybe. Yeah. But so that would kind of, in some sense, be more or less secure, given that, so it is the low priority task is protected against higher priority interrupts. But that's one must be a little bit careful. It works fine if all of these interrupts have the same priority. If there are interrupts with different priorities, then these interrupts could interrupt each other, and that would again cause problems. So it is it's not very safe. But they have then these two levels, so it's fine. So it seems fine to them. So maybe it's ordinary. I don't know what they think. So now, what would we do with such programs? So the current status of our analyzer is that, as I said, globals are flow insensitively, and that is nice because then you can do this interprocedural analysis. But this flag variable then takes values 0, 1, and if you do interval analysis, the best you can hope for is the interval 0, 1. And you do not know which of the values will be there. And that means that you cannot exclude that both execute their critical sections in parallel. This means that the defense priority of a variable accessed in the critical section would be low and the offense would be high, and that would mean we would see a data race and, a false alarm. So if one wants to get rid of such kind of false alarm, what could one do? So our idea is first that one would have to identify the flag variable. So there are two. So there's a very quick answer. The very quick answer is throw away the global invariants. So kind of track the values of global variables flow and context sensitively. One could do that. The problem is that there are many of them, and often their values are completely boring and do not have much effect because they depend on input data or they simply don't influence the control flow, and therefore that would be possible but expensive. A better way would be just to track this few variables, flow and context sensitively, and as few variables as possible. And the best thing is only to track these flag variables in this way. And how can we do it? For that one would have to identify these, and and then once one has identified these, one would deal with them, and then one would define the notion of data race. So how would one identify a flag? So first, the thing interesting is that the access to the flag is also a data race, because one somehow assumes that this writing to the flag and reading from the flag is more or less atomically and interrupts occur afterwards. Otherwise, they would kind of interfere. But since writing 0 and 1 is, it seems that they don't worry about this kind of data race. And but the assign, so this is one indicator for a flag variable. The other indicator is that the assignments to these are very simple. It's just some constant value, probably not only 0 or 1, maybe from some kind of enum kind of state or whatever they think they might be useful. So that would kind of, these constant can be more or less easily, I would think that these can be, by a constant propagation, one would be able to identify these. And yeah, then once one has that, one would kind of extend the interprocedural framework in such a way that one now tracks the values of these flag variables, but now interrupts matter because the interrupt may read it or write it, but in that sense one now has to kind of extend the interprocedural analysis to an analysis which is additionally interrupt aware. And that means you have at every program point you have to insert the possibility of all interrupts possible there. And then once you have this interrupt aware analysis framework, then you can do constant propagation for these flags. And then using this extra information, one would define a refined data race as something where the defense of X for a given flag status is less than the corresponding offense priority for X with this particular flag status. And again, there could be many flag statuses if you have several flag variables, which could be exponentially many or what, but one might just track that for those flag statuses which really occur in the program, which again, typically I would guess are few. So maybe, so how long should I talk? Should I finish or should I continue?
10 minutes.
10 minutes, okay. So then perhaps a little bit more. So that was all which I wanted to talk to you about these concurrency bugs. But one might also search for other runtime errors, and for that one would have to look at the values of variables more in greater detail. For this user-defined protection mechanisms, we also had already to look at the at the values of variables. And actually, when I told you that we have provided an implementation in Goblint, the Goblint analyzer will not just follow the program points and the control flow, but will always analyze data also. Because as you know, probably it's like, so I think in German what you say, carrying owls to Athens. So when you analyze C, you must analyze data and pointers, and otherwise you are doomed. And so this we already do there also. And then, yeah, and so this would be two cores, so that one needs a kind of framework where interrupts are taken into account too. And that so what would that, how would one possibility to do that is whenever, so as I said, at every program point you insert kind of such a preemption operator which summarizes all possible interrupts at that level. One only has to take into account that dynamically, that the priority is dynamic. So the interrupts which are admitted are dynamic. So the analysis also must kind of depend or propagate the current the possible dynamic priorities when reaching a program point, because only then you know what kind of interrupts will occur or possibly can occur. And then you have to do that at every program point. And then that is the things then what we did with Markus from Münster. We looked at one particular benchmark value analysis, which is linear equalities. And then in this setting, one can show that one can exactly analyze linear equalities by using summaries for procedures or interrupts, which are mappings from resource sets to, if you linear to vector spaces of matrices. So each matrix kind of tells you for how the function call will transform a linear equality before into a linear equality afterwards. And since there are many runs through the procedure, you could have many such linear transformations, and the best approximation of all these is kind of a vector space of these. So therefore, a vector space of matrices. And so maybe I kind of will not go through this example, but only tell you that it's such kind of analysis, you can deal with that. And again, this interprocedural analysis will be linear in the size of the program. It will heavily depend on the priority levels and on the number of resources, because you have to track, to distinguish the different priority levels and resource sets. But it will be polynomial in the number of variables. Okay, polynomial probably in practice, polynomial if it is exponent, I think in theory it is exponent 6 or so in the number of variables, and if you think of C with perhaps hundreds or thousands of globals, then you might not feel comfortable with it. But if you use sparse matrix representations, it is not as bad as one. So we have an implementation, well, not in Goblint, but in another analyzer, and made experiments with these linear equalities and these vector spaces of matrices, and it was quite fast. Okay, so thank you very much.
So what makes linear equalities a good abstraction for tracking?
Why linear equalities? What it is good for? So that is so we use here in that sense here it is I would say a benchmark analysis to check what one can do with the framework, and whether the framework for these interrupt-driven programs, whether you how different or how similar it is to classical, to ordinary interprocedural analysis. What we have used this, where this linear equality analysis is very important, is probably not in this context, but in the area of when they analyze binaries. Because then you get, by that you find out things like constant offsets, and how things depend on the stack pointer, for example, and by that may recover local variables, which is very important in order, and then you can, well, if you're an analyzer, then tracks register values also, which is perhaps the closest to local variables or global variables here. And then there, in any program, you will have two instances of the same program variable, one in register, one on the stack, and you have to relate them by an equality. This again introduces inequality. So tracking variable equalities is very important when you analyze low-level code. Yeah. I think there are, but that's the first one which spontaneously comes to my mind. But it seems so that people have used, for example, if you think constant propagation, linear constants, and all that, these are all very simple cases just of linear equalities.